Okay, titration. So in a titration, this is a fairly typical titration setup. This is titrating an acid. You'd have some sort of unknown that you would place into a beaker. You'd know the volume of it. You'd put it in using some volumetric pipette. You would then do that titration. You'd have a titrant. In this case, it's standardized sodium hydroxide. You know the concentration here. You know chemically what happens here. You know the stoichiometry in here. So you've got a unknown concentration, known volume, measure a volume, know the concentration, figure out the concentration of the unknown. All right, you got a final reading, and you got a neutralized solution, and you got the indicator changing colors. Well, a titration and an acid-base titration, the solution of known concentration, titrant, is slowly added to a known volume of a solution of unknown concentration, titrate, from a burette until the reaction is complete. So when the moles of titrant equal the moles of titrate, the titration has reached an equivalence point, because I've got equal moles of titrant and titrate. An indicator can be used to determine the end point, and an indicator is just a chemical that changes color when the pH changes. The end point is an observed titration, right? There's a difference between end point and equivalence point, right? End point is when the indicator changes color, and equivalence point is when the moles of titrant and moles of titrate are stoichiometrically equivalent, right? So the end point is an approximation of the equivalence point. The equivalence point is the thing we really want to get to, but the end point is oftentimes our best handle on getting to it. You can do all kinds of different titrations out there. You can do acid-base titrations, and that's what we're going to focus on. You can do electrochemical titrations, redox titrations, back titrations, titrations to determine nitrogen content, complexometric titrations like EDTA for water hardness, and many, 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 many more. Right, but let's look at the acids and bases ones, and that will more than whet your appetite for doing titrations, I promise. All right, so with acids and bases, there are 4 different options, right? Depending on what I've got in my burette and what I've got in my flask. Right? So in my burette is usually what's going to determine the type of titration I'm going to do. So if I do something that's a strong acid or a strong base titration, that's going to refer to the titrant, because that's the thing you know the most about, right? You know the concentration of the titrant, you know what it is, and you measure how much you add in. The titrate can be lots of different things. That's got more variability to it. You can probably fix the volume that you've got, but you won't know the concentration. You might not even know if it's a strong acid, or you might not know if it's a strong titrant or not, right? So it could be if it's a strong acid, and it could be a weak base, or it could be a strong base, and you may not know that right away. Right, so we've got 4 different pairs that we can have for a titration. So I could have a strong acid and a strong base. I could have a strong base titrating a strong acid. I could have a strong acid titrating a weak base. Or I could have a strong base titrating a weak acid. Right? And they're all going to generate these kind of sigmoidal curves, sigmoidal meaning S-shaped. It kind of looks like an S. And if I've got a strong base in my flask, my pH is going to start up really high, and then as I neutralize it, boom, it's going to get to 0, and then it's going to be a really low pH when I've got excess acid. And the opposite happens if I've got a strong acid being titrated with a strong base. It's going to start off really low and then shoot up real fast, and then go kind of flat as it just has the strong base in solution. If I've got a weak base in solution, it's going to follow this kind of stretched out sigmoidal curve, right? So I start off with a weak base. It's going to be basic. pH will be up above 7, and it's going to stretch out for a while and then go sharp and make a real sharp curve and flatten out at a low pH, right? And the opposite will happen with a weak acid being titrated with a strong base. Right, so it's going to start off low, stretch, and kind of go flat for a little bit, and then shoot up and flatten out again. Right, so and we will look at the different areas on each of these things. Right, what you do not want to do. Right, so you don't want to take a weak acid or a weak base and put it in your burette. That's a big no. You do not do that. Right, your titrant has to be the strong thing. It's either going to be a strong acid or a strong base. Right. Our basic setup is going to look like this. And there's a titration set up for an acid-base reaction. So I've got the beginning of a titration. I just have H plus in here. So this is titrating some sort of acid with a strong base. So I've got sodium hydroxide in here. I drop in some, in a controlled fashion, some of the sodium hydroxide. It's going to change this indicator colors at the equivalence point, and this is a really bad version, so somebody did not do a high quality titration here. I'll have excess hydroxide or just pure water, and I'll turn my indicator pink because I'm using phenolphthalein as an indicator. And so you have probably done this in 1211 to determine the concentration of a titrate, but we're going to do a pH titration where we're going to monitor, because now that we've got pH as part of our toolkit, we're going to be able to monitor the pH as a function of added in titrant. So this equivalence point here we said was this endpoint was an approximation of the equivalence point. This should really be endpoint in here. And they are showing that as an endpoint, not the equivalence point. We will find that using the pH to monitor our titration's progress is actually going to let us determine the real equivalence point rather than just the endpoint. Okay. So the general method for monitoring the pH during the course of our titration is to measure the conductivity of the solution due to the H3O plus ion concentration. We do that with a thing called a pH probe or a pH meter. Right. It's going to be specific to the H3O plus ion concentration. Right. And so we will add in our titrant and we'll monitor the pH as a function of added titrant. So as this becomes added, this is my x-axis and the pH is my y-axis. So we're going to, for our titration curve, that's a plot of pH versus the amount of added titrant. The inflection point on the curve is the equivalence point of the titration. So this actually gives us the real equivalence point where the moles of titrant and moles of titrate are equivalent to each other. So prior to this, the known solution in the flask is in excess. So it's closer to its pH, and afterwards it's going to be closer to the pH of the titrant. Right? The pH of the equivalence point is going to depend on what you've got in solution. Right? If I've got a neutral salt, right? So if I'm doing a strong acid, strong base titration, my pH is going to be 7. If the equivalence point is of an acidic salt, the pH is going to be less than 7. So if I did a weak base and I titrated it with a strong acid, at equivalence I would just have the conjugate weak acid in solution. It will be slightly acidic. If I've got a basic salt, like I titrate acetic acid with vinegar with sodium hydroxide, right? At the equivalence point, I will just have the acetate in solution. That's a weak base. The pH is going to be bigger than 7. So beyond the equivalence point, the solution from the burette is in excess, and the pH is going to approach that of the titrant in the burette. And we'll never quite reach it because you'll have some sort of dilution factor. All right, so let's talk about indicators for a second. Indicators are useful for identifying those changes in pH. The pH meter is going to be better. But what is an indicator? Well, an indicator is a weak acid or a weak base that's going to have two different colors depending on whether it's in the acid form or whether it's in the base form. So whether it exists as the conjugate acid with the proton on it or whether it exists in the deprotonated form as the conjugate base. So this just like we've got HA or HX, right? We've got HIN, that's the indicator, that's the base part, the conjugate base part, is going to react with water to form H3O plus, and then the conjugate base form IN minus. So if I've got something like phenolphthalein, this is the phenolphthalein indicator, it's got a colorless form where it's acidic. So there's this this group here that's going to form this little oxygen bridge between these two carbons, and that's colorless. If I stick a proton on there, all right, now I've got this carboxylate group where it's like a carboxylic acid but without the proton, and this form is pink. And if you take some advanced chemistry classes, you will figure out why this guy is colorless and why this guy is pink. But this is a weak acid, so it's going to have its own Ka value, right? It's going to have its own Ka, and then it's going to have its own pKa. And the pKa of that indicator is going to be roughly equivalent to where it's going to change pH, or it's going to change from one form to the other. So pH is going to be pKa plus the log of In over HIN. I can do the ratio of those, in this case, the pink form to the colorless form is 10 to the pH minus pKa. That's going to give me the range over which we're going to see that color change. And so here, if the ratio is 10 to the 0, or about 1, it's going to be some intermediate color. If pH is equal to pKa plus 1, it's 10 to the 1 or times 10. It's the color of the indicator. Or if it's pKa minus 1, it's going to be 10 to the minus 1 or 0.01. It's the color of the acidic form, colorless, right? So when it's right about at the pKa, then it's going to be this intermediate color, which for the phenolphthalein is this pale pink color. Right? And we've got lots of different indicators. So here's methyl red. It's a different indicator. It's going to go from this red color to a yellow color, and it's going to kind of be an orangish around pH 5. Right? So red and yellow make orange. So this is the intermediate form. And so it's an indicator that changes at about pH 5. So if we've got a nice sharp transition between, where your pH really shoots up from like 4 to 8, well, then that would be an okay indicator for you to use. Different indicators have different range over which they are effective. Right, so if your weak acid, say, is going to have an equivalence pH of around 3, erythrocin B might be an indicator for you to use. Right? It's going to be colorless, and then red, and then colorless again. And some indicators have more than one color range, like thymol blue here. It's going to go red and then yellow, and then it's going to go from yellow to blue again. And so depending on what your titration is, you're going to have different indicators to choose from. Now for a strong acid, strong base, right, something like phenolphthalein is usually going to be a good idea, because you're going to either end up with a strong acid, right, so down here, or a strong base, and your titrant's going to be a strong acid or a strong base. So the transition is going to be pretty sharp. Right? So phenolphthalein is a good indicator for that. It also works around a pH of 8, so it's going to be okay for something like acetic acid. Right? So many dyes change color depending on the pH of the solution. That's actually one of the ways that they do those color changing cups and plastics, right? You get the Freezy cup, and it goes from like white to blue, or like you put it in solution, it goes from like orange to green or something. Those are actually pH sensitive dyes, and what's happening is that you've got the dye molecule, and because K is dependent on temperature, pH is dependent on temperature, the degree to which you've got the protonated versus the unprotonated form of the dyes changes, and that's how they end up changing color. The dyes are weak acids, and they're in equilibrium with the H3O and H2O in solution. The color depends on the relative concentrations. Right? If you're about 1, it's a mix. If you got more than a factor of 10, the color is going to be a mix of the colors, primarily with the IN minus, and if you're at less, it's going to be mainly the protonated form. Right, so the end point is where this indicator changes color, right? But it is different from this full titration curve. Right? So an indicator is useful if you want to get a rough approximation of this. It's going to be plus or minus a little bit, right? Because it's going to change color over a range, which means I've got a very small range over here on the x-coordinate. Right? But for most titrations, you're going to have a very large pH jump at some point, so a lot of indicators are going to be useful. Right? So you want the pKa of the indicator to be about at the pH of the equivalence point. So for example, here we've got a strong acid. pH is really low. Being titrated with a strong base, we end up with a pH that is high. I've got a really sharp jump. Just about any indicator is going to work, so methyl orange would work, or phenolphthalein would work.